Hello, Brian Miller-Hicks here. Today, May 18th, 2025 is a special day for me and for many geologists, especially volcanologists in the Pacific Northwest, because 45 years ago, Mount St. Helens erupted in a very powerful, disastrous eruption some 45 years ago on May 18th. 1980. So the year after, 1981, I was fortunate enough to be a graduate student at Oregon State University, and I was lucky enough to hook up with my then thesis advisor, Dr. Frederick Swanson, and we and some colleagues and my girlfriend at the time, my future wife, Kathy, had an opportunity to go to Mount St. Helens the year after it erupted and do some research. Now, I don't know exactly where Dr. Swanson got his funding from. I think the USGS, Oregon State University Forestry Sciences Lab. Dr. Swanson was a geomorphologist, geologist, and forestry science geologist, and he was kind of looked like John Muir as a young man. So he was an interesting fellow, guided me through the whole master's thesis process. I owe a lot to him. So what you're seeing here is Mount St. Helens in 1981, thereabouts, still actively steaming, sending water vapor up into the air. Of course, a snow-capped, beautiful peak, even though it's some 1,300 feet of it was destroyed in the eruption. And here you can see a lava dome building that will eventually lead to the rebuilding of Mount St. Helens into the beautiful round top, more or less, peak that we knew before the May 1980 eruption. Here's Mount St. Helens some 45 years later. You can see the recovery, the greening of the terrain in front of the volcano, in front of the northward trending eruption. Plants and animals are coming back. Mount St. Helens eruption in 1980 proved to be an extremely useful, very great opportunity for scientists of many disciplines to come together to study not only the volcano and the volcanic processes and the eruption, but to study the recovery of an area that has been devastated by a volcanic eruption. So not only were there geologists, there were also biologists, botanists, entomologists, fish experts, scientists of all sorts of disciplines. So it's really a unique living laboratory of how nature comes back from disastrous events, and we're learning a lot. So I'm not going to go through the whole sequence of events of the eruption. There's tons of TV documentaries, of YouTube videos, all sorts of books and magazines and pamphlets you can read. So I'm not going to belabor that. Mainly, I'm just going to be talking about my experience going to this amazing area in 1981. So here's sort of an intro or a refresher course. On May 18th, 1980, the mountain erupted disastrously. A large earthquake caused by movement of magma, presumably underneath the volcanic cone, loosened primarily on the north side of the volcano, loosened rock, caused a gigantic landslide to move northward, taking much of the mountain down with it. And that caused an opening and released tremendous pressure of hot gases and hot water vapor to erupt rapidly, mostly laterally or northwards, but also up into the air, sending mud flows, sending ash eruptions, pyroclastic flows, shattered rock, etc. The whole gamut of volcaniclastic or tephra type materials from an active volcano. So here's a map of the eruption damage. Here's the cone, the crater. Again, the eruption was primarily northward. Here's the north arrow. This is the blast zone where nothing in that area survived, whether it was a tree, an animal, or a human. Poor Harry Truman is buried somewhere beneath probably hundreds of feet of the landslide that collapsed from the mountain. This is Spirit Lake, on whose shores he had a house. Over to the northwest, this is the tree blowdown area where the hot winds and force of the eruption blew down thousands and maybe millions of trees. Forest that was standing, living, thriving, healthy, just fell over in this area, as well as this area here. Debris flows from the eruptive deposits of mud, ash, rock, snow, ice that melted during the eruption came into the North Fork of the Toutle River and the South Fork of the Toutle River, sending much mud, water, and debris to devastating effect, wiping out logging camps, wiping out vehicles, wiping out bridges, highways, roads, killing people, etc. So the total human cost of this eruptive event was 57 lives, and of course millions of animals, plants, insects, etc. Okay, so here is a picture I took when I got up there. This is looking southwest towards the blast crater. Here's the blast crater right here, and you can see there's still steam coming out of that blast crater. The volcano is still in very much of an active phase. This is a valley in the area where we were walking around. It's filled with volcanic ash, shattered rock, sand, pumice, and of course the devastated, destroyed, blown down, and killed trees as well. This is an interesting photo showing in this sunlit area that the energy of the blast from the eruption came racing up this hillside, killing these trees with heat and wind, but leaving them standing. So this wasn't the major or maximum force, but it was a force enough and enough heat to kill these trees and leaving them to stand in their position. Right here you see the boundary. Over here the trees are still green and healthy, although they're coated with ash. Anyone that walks up there will see that. And down here the killed trees in the devastated area. Here's a typical view. I did not take this photo. I got it from somebody else. This shows a typical layering of the volcanic deposits from an eruption, such as Mount St. Helens. Down here, we see what's called blast sand. So blast sand, and we saw this when we were digging through the recent deposits from 1980. Blast sand is shattered rock and minerals that are forcibly just powdered or turned into sand, if you will, and just thrown out forcibly by the energy and power of the eruption and then deposited in a wide area. On top of that, we get the lighter airborne deposits of ash, which took a little longer time to settle. They're not as heavy as the sand. So the ash took some time to settle down above the sand deposits. And the pumice, which, as you know, is fragmented volcanic clastics material that are permeated by hot gases. And if you pick up a piece of pumice, it's shot through with pores or vesicles. And a piece of pumice is quite lightweight because it's got all these holes formed by hot gases coursing through the material. So blast sand, ash and sand, and then pumice on top, which was the last to fall because of its light weight, floating around in the air for some time before it finally settled down. This is Dr. Swanson again, and two of my colleagues that were with us on this great research adventure. We wanted to survey the nature and thickness of deposits at various points that had been devastated by the volcano. What Dr. Swanson wanted to see was whether there would be any difference or contrast in erosion in the deposits that were found in clear-cut zones versus deposits found in formerly forested zones. As I mentioned, Dr. Swanson was affiliated with the Forest Service of Forestry Sciences, so his mission was to collect data on the rate of erosion and the expected results of contrast between those two different types of areas. So having to traverse this terrain was, as you can see, quite challenging and quite difficult. What we did was at each data point we pounded in steel rebar and then dug small pits to measure the thicknesses of the pumice deposits, the ash deposits, and the blast sand deposits in certain areas that were selected as we went. This is me over here. Well, these photos were from a local newspaper, I believe a Portland, Oregon newspaper. So I'm digging through these recent volcanic eruption deposits. And this is me again. I had a lot more hair back then and also a mustache. And this is my beautiful girlfriend at the time, now wife, Kathy. And I am calling out to her the thicknesses of the various types of deposits so she can record the data. So how did we access some of the more difficult areas? We took a helicopter provided by Oregon State, maybe the U.S. Forest Service and USGS. I actually don't remember. So this was a helicopter piloted by this gentleman on the left, who is actually a Vietnam-era military pilot, helicopter pilot. And this gentleman here is Dr. Swanson. Here we are in one of the ridge areas, I think to the south of the volcano, which is in a clear-cut area. You can see that from the stumps that this was a former clear-cut area. There's not many or any standing trees. There's relatively few trees. And this area, of course, is covered with volcanic eruptive deposits from that event. So our mission was to collect initial baseline data of thicknesses of deposits, and then the idea was to come back over the years later to see how these deposit thicknesses were changing due to erosion from water and wind and gravity. I went only 1 year, 1981. I presume Dr. Swanson sent crews of students up there in later years to get more measurements. So just to give you a basic idea, what we found in these baseline measurements was that areas of deposits in clear-cut areas were heavily eroded by rills and streams and cut through to quite some depth, whereas areas in down trees which had not been clear-cut but were just trees laying down on their side. These trees constituted dams where sediment would build up behind them and perhaps preserve more of the deposits without being eroded away. So clear-cut erosion was greater, even in that 1 year between 1980 and 1981, and erosion in just down tree areas was less. Here's the south side of Mount St. Helens. Here's a helicopter. You can see the active venting of steam. You can see, even though this is the south side and most of the eruption took place to the north, some pyroclastic flows and other hot winds and gases came down the south side and wiped out a bunch of trees in this area as well. Here is Spirit Lake, just north of the volcano. All these small fragments that look like small fragments are floating trees and logs. These muddy looking patches are deposits of debris from the eruption, so rock, sand, etc., that fell into the lake. The whole lake level was increased in elevation a couple hundred feet, as I recall, and turned the lake into quite a different character type lake. Initially very toxic water, but now from reports I've read, it's cleared up quite a bit, although you can still see rafts of millions of floating logs in the lake still. Here's another view of the south side from the helicopter. You can see this notch in here was formerly occupied by a glacier before the eruption. And here we are in the helicopter actually cruising into the blast crater and cruising and circling around an actively building lava dome in the blast crater. This was very thrilling and exciting, and maybe a little dangerous. Even in the helicopter, we could smell sort of the sulfurous odors coming from this, from the steam and gas emanations. So we just quickly circled around and then exited. So this was something I'll never forget. This dome, of course, has been building constantly from 1980, and may eventually fill up the entire crater and plug it up into a volcanic cone again. It goes through different stages of surging and building and collapsing in and on itself, but it's a continuous rebuilding process, and that's apparently typical of these types of cascade volcanoes. And just a farewell shot saying goodbye to Mount St. Helens. It was devastated in 1980, but like all things in nature, nature recovers and heals. Animals are coming back, plants are coming back, insects are coming back, people are coming back. There's a thriving tourist industry of people wanting to see the volcano. And they've built a volcano observatory named after the geologist David Johnston, I believe, who was killed during the eruption. Thank you for watching.